Hi, I'm Andrea, and our work is on learning features from human input for improving reward learning. Robots can adapt their behaviors by learning from human input, like demonstrations or corrections. For example, here, the robot starts off with a trajectory obtained by optimizing some pre-specified reward function, typically encoded as a trade-off theta between important features phi of the task, things like distances to obstacles or efficiency. Now, as I see it perform the task, I'm pretty unhappy with how high above the table the robot is carrying the cup. So I can push on it to correct it. Prior work shows how the robot can interpret human input like this as evidence about what people want and update its understanding of the reward trade-offs data. The robot can then optimize this new reward function to perform the task in a way that's closer to what the person intended. This works pretty well when the robot's feature space carries everything that the person might possibly care about. But what if that's not the case, as it usually isn't in the real world? Here, I want the robot to stay further away from me, but it doesn't have a feature for that. I could push it, but at best the robot will just recognize that it doesn't have the features necessary to interpret my input. In our work, we ask, how can we teach the robot the right reward when its feature space is insufficient to capture what we want? To answer this, let's have a look at an example where the person cares about being efficient and keeping the cup close to the table and away from some laptop. If we imagine the table as the ground plane, spatially the human's reward might look something like this. The lowest reward in yellow is right above the laptop and high above the table, and it gets better the closer to the table and the farther from the laptop we look. Meanwhile, the robot knows about some of the features, but not all of them. In this case, it's missing the distance to the laptop feature. We want the robot to somehow learn this missing feature and how it combines with the remaining features into the reward. Recent advances in deep inverse reinforcement learning, or IRL, suggest that we can do both steps at once using deep learning. First, model the missing feature as a neural network mapping directly from the high-dimensional raw state of the robot and add it to your set of known features. Then, collect some demonstrations of the task from the human and use them to both extract what's missing implicitly and learn a state reward. The final reward is then given by the sum of the trained state rewards. Now, when we follow this procedure, we see that a maximum entropy IRL method does a reasonable job identifying approximately where the laptop is, but it can't really learn a more fine-grained detail of the reward function. So what's going on here? What's wrong? Well, the demonstrations that deep IRL use are meant to teach the robot how to do the task. They aren't meant for feature learning per se. So with this neural network structure, the method is just kind of hoping to learn the missing features implicitly from the demonstrations. But by trying to both extract salient features of the task and learn the reward on top of them all at once, DeepIRL ends up generalizing pretty poorly. So what if, instead of trying to do everything at once, we first focused on learning the feature by asking the human for some sort of input about it, and only then learn the reward on top of it using task inputs like the demonstrations or corrections that we talked about? Our key insight is that instead of learning about the missing features implicitly, the robot should ask for data that explicitly teaches it what is missing. So how can we actually teach a feature? A natural first idea would be to still model the feature as a neural network, but then ask people for labels directly representing the feature value at certain states in the environment. After all, what is more explicit than supervising the feature directly? After collecting a data set of regression labels, we could use it to train the neural network via supervised learning. Unfortunately, to learn anything useful, the robot would need a humongous set of labels from the person, which would be way too burdensome. Even worse, humans can be fairly imprecise when labeling the states directly. But it turns out that we can actually do a lot better than this. Instead of having the person label states independently, we can pack a lot more information if we ask the person for a sequence of states with feature values that are monotonically decreasing. We call the sequence with this property a feature trace. So in practice, to teach the robot at that distance from the laptop, I start somewhere where the feature is highly expressed, above the laptop, and move the robot monotonically towards a place where the feature is not highly expressed, away from the laptop. After the robot collects a few of these traces, it can learn a feature function defined by them. The The beauty in these feature traces is that there's a lot of inherent structure in them, and we can harvest that to learn a feature effectively. First, we have the feature trace's monotonicity assumption, where the feature values decrease along the states of the trace. Next, we know that all traces approximately start at high feature values and end in low ones. So for these two traces, this means that the start labels have to be consistent with some L0i, which by default is 1 for high feature values, but that can be provided by the human optionally. And the same for the end states, this time with a default value of 0 for low feature values. And lastly, humans are imperfect, so we model them as noisily rational according to the Bradley-Terry and Luce-Shepard model. Armed with these three properties, let's see how we can convert feature traces into something that our neural network can actually learn from. By exploiting our assumptions, we can transform the feature traces into a data set of tuples suitable for training. For monotonicity, we take any ordered combination of two states along a trace and label them 1, meaning the first state in the tuple has a higher value, and we do this for every trace. For the second assumption, we essentially want all start labels to be indistinguishable from one another, and the same for the end labels. This gives us tuples with a label of 0.5 to symbolize equivalence. And lastly, we incorporate this data set of tuples and the human modeling choice into a simple cross-entropy loss for training the network. We now put our feature learning algorithm to test in a case study with expert users and a real robot manipulator, as well as in an online user study, recreating our lab environment in a simulator. In all of our experiments, we tested the algorithm by sampling a test set of states in the robot's reachable set, and comparing the FERL output against ground truth. For visualization purposes, we can project the learned feature onto a representative plane like so. Qualitatively, when we look at the ground truth laptop feature, we see a projected ball that decreases in intensity the farther from the laptop we go. FERL, turns out, learns a qualitatively very structurally similar feature. And this result holds across 6 different features that we tested with our method. Quantitatively, we took the mean squared error between the ground truth and the learned feature values, and we plot that with a varying number of traces in orange. The standard error bar is across 10 different subsets of feature traces, and the gray line represents the mean squared error for random feature values. We observed that with enough data, FERL learns features much better than random, and with more data, it both learns increasingly better features and becomes less input sensitive, as seen by the overall decreasing standard error. Next, we tested FERL's efficacy for reward learning. We compared the previously mentioned DeepIRL baseline to our method, which first learns the features from the traces and then the reward from corrections. We tested 3 cases where the robot has access to 2 known features, and we varied which of the laptop, table, or proxemics feature was the unknown one. The true reward depended on a combination of 1 known and 1 unknown feature. In all of these cases, FERL is better able to learn a fine-grained reward structure than DeepIRL. Quantitatively, when we focus on one of these 3 cases, we see that FERL is better at learning generalizable rewards, shown by the lower MSEs, and is less input sensitive than the DeepIRL method, shown by the lower standard error. And these trends hold across all of the 3 cases. Lastly, we ran an online user study to see whether FERL works with non-expert users. The study was over Zoom, and people provided feature traces by clicking and dragging the robot in the PyBullet simulated environment shown over here. We found that FERL was able to learn good features even with non-expert user data, as the MSEs for the user features are much closer to the expert level than to the random one. Next, we took these user-taught features and performed reward learning with the expert corrections. We see that even though DeepIRL was given the advantage of using physical expert demonstrations, not simulated ones, it still severely underperforms when compared to FERL with both expert and user features learned in simulation. Together, our results provide evidence that FERL's divide-and-conquer approach of focusing on what's missing explicitly before learning the reward is more effective than learning everything at once implicitly. Thank you very much.